Thank you. Yeah, last talk of the conference. Thank you so much to the organizers for the invitation. And yeah, let's get into it. Okay, yeah, so I am at Los Alamos National Laboratory, and I'm going to be presenting on work done in collaboration with my co-authors, Andreas Berchi and Stefan Eidenbenz. We are specifically in the Information Sciences Division at Los Alamos National Lab. Okay, so over the summer, this last summer, there was a paper released by IBM Quantum. The citation for this is at the bottom of the slide. You may have heard of it. The title is Evidence for the Utility of Quantum Computing Before Fault Tolerance. And they basically performed a series of very large experiments using 127 qubit quantum processors that they have developed, Quantum has developed. These are digital gate model processors. They used a number of techniques to kind of improve the computation. So one is this technique called zero noise extrapolation. Zero noise extrapolation is basically the idea is actually reasonably straightforward in that you can make a circuit works basically. So if you have some logical circuit and you run it on your quantum computer and it has some noise, well, you can just essentially double the size of the circuit while still performing the same unitary. And then you have 2 times the amount of noise. Then you can do that for 3 times and 4 times. And then you can just extrapolate back to where your zero noise point should be for some observables. So this only works if you're quantifying like some real number, some cost function, for example. It doesn't work for bit strings. Yeah, so they looked at a couple of different observables. So some were just kind of arbitrarily chosen Pauli strings. They also looked at magnetization, specifically single-site magnetization on this lattice. And the Hamiltonian dynamics that they were simulating were TFIM, a relatively straightforward ferromagnetic system native to their Heavy-Hex lattice topology. Yeah, they also use things like Pauli twirling, things like this to kind of improve the computation. Okay, so this is kind of somewhat of a somewhat simple physical system at TFIM, but the circuit description that they used was a trotterized first order trotter decomposition of what this Hamiltonian simulation should be. And they kind of made it very, very kind of hardware native, nice to run on the gate model processor. And this is what the Heavy-Hex graph looks like, the 127 qubit Heavy-Hex graph. As you can tell, it's quite sparse, right? So they defined this problem to be, like I said, completely native to the lattice. So once they released this, there were kind of a large series of subsequent papers that came out about various ways to do simulation of this system pretty fast. So in the paper, the reason that they argued that this was evidence for quantum utility was because they utilized some, for example, MPS simulations that failed just because of basically memory and or time requirements. That was the argument in the paper. And then there were basically, I don't know, at least maybe 4 distinct types of approaches for simulating the system, including MPS, some kind of light cone simplification arguments and stuff like that. So yeah, there was kind of a large number of simulation techniques that came out. And to be clear, when we say efficient here, like on the order of minutes or hours, something like that, in order to compute these observables that IBM looked at. Okay, so our contribution is to use programmable quantum annealers to look at the dynamics of one of these observables that IBM was able to measure, magnetization. So our preprint is live on arXiv as of a couple days ago. That arXiv link is at the top of this slide. This simulation was relatively non-trivial to pull off. There's a number of different aspects of it. I'll walk through all of the main kind of complicated and interesting ones in this presentation. But one of the most basic ones was just getting the Heavy-Hex graph onto, say, the D-Wave Pegasus architecture. We had actually already done this for a QA, short-depth QA OA circuit in a series of papers last couple of, like, nearly a year ago. And those papers are cited at the bottom of the slide. Yeah, so in particular, the simulation that we were doing is we derived equivalent parameters to the IBM Trotterized experiment. So we tried to make the simulation kind of as faithful as possible to the original IBM experiment. And that, so it turned out to be possible on D-Wave, which was not necessarily expected. There were a number of kind of energy scales that had to line up for this Hamiltonian simulation to work. Okay, so the next like 5 slides are going through this derivation of how this works. So, equation 2, this is the Hamiltonian that IBM simulated. Right, this is the Hamiltonian. Okay, so their simulation is kind of a lot of very specific details, but they basically evolved this system for a total time t, which is equal to some n number of time steps, or Trotter steps. In this case, the number of time steps and the number of Trotter steps are the same. And if you increase n, if you increase the number of Trotter steps, you're also increasing the number of time steps. Yeah, and I'll explain why that is in a few slides. So n denotes simultaneously the number of Trotter steps, right, and the total evolution time. All parameters are unitless. Okay, this is the circuit description of what the IBM circuit actually was. So this is essentially a series of layers of RZZ gates followed by single qubit Rx rotations, parameterized by this variable theta h. Experimentally, in the IBM Q experiments, what they did primarily was vary theta h. This is a kicked Ising simulation, so when theta h is 0, you expect, for example, your magnetization to be all spin up. And then as you vary it closer to pi halves, it gets closer to 0. So the particular construction method was, again, this was based on the Heavy-Hex graph. Now the nice thing about the Heavy-Hex graph is that it's quite sparse, so you can do a 3-edge coloring on the Heavy-Hex graph. And so what that means is that you can place your 2 qubit gates in parallel on each of the 3 unique colors, giving you a 2 qubit gate depth of 3 per layer, which is pretty short depth. Additionally, they fixed the angle of the RZZ gate to always be negative pi halves. This gives you a very nice simplification because now you only need one C0 or one 2 qubit gate in general to implement this RZZ gate. So you've essentially cut your number of 2 qubit gates in half, making it even nicer to run on the hardware. Right, so our goal is to implement the simulation of the same original Hamiltonian, but on D-Wave. And we simplify the problem by only considering schedules with very fast quenches. This is a simplification, and it's not always accurate. The quenches are just a necessary part of kind of the engineering of the system that we have to have because we need to quench to kind of read out the qubit states, and if we're using reverse annealing, we have to initialize in the classical spin-out state. But neglecting the quenches, for simplification, this is the Hamiltonian simulation that we kind of aim to implement. Right, so we implement the simulation for some annealing time, here we call it TQA. And we have the functions A of S and B of S, which are given to us by D-Wave, right? This is kind of a machine dependent. And we specifically test this on Advantage Systems 4.1 and 6.2. Those are the chip IDs. So for J, for the coupling strength, so again, going back to the original problem, here J, it's a ferromagnetic coupling strength. So we can program J to be whatever we want, but there are hardware limitations, right? There's finite quantization of the problem coefficients. So if we program J to be, for example, too close to 0, it will be effectively like you're just setting the coupling strength to 0, and that's not good. Right, S is the anneal fraction. Ratio A of S over B of S is kind of our S. And for a kind of a linear, forward annealing schedule, this is monotonically increasing. A of S and B of S, A of S over H and B of S over H are device-specific functions, again calibrated by D-wave. And we say that our annealing time is in microseconds. So our goal is for any given theta H, so again, theta H is the parameter for the single qubit Rx rotations, right, in the Trotterized circuit. So this is essentially driving how much of the transverse field Hamiltonian we have. Our goal is for any theta H to program the equivalent N, which is the number of Trotter steps, which is also equivalent to the number of time steps in this case. And to set our J to some reasonable coupling strength that we can actually program on D-wave. And our S, which is our anneal fraction, and our annealing time, such that we evolve the equivalent Hamiltonian to what the IBM experiment did. Yeah, so by the way, just to be clear, if you're familiar with Trotterization, usually, if you increase the number of Trotter steps, what you're doing is you're doing a finer discretization of that Hamiltonian simulation. But in this case, in the IBM experiment, because they fixed the angle on the RZZ gate to be negative pi over 2, this is not actually doing a finer discretization. This is actually just doing longer evolution times. So as our n increases, this actually corresponds to just evolving for a longer time, which when programming on the quantum annealer, this is just a longer annealing time. So that's fairly straightforward to do. Right. Okay, so yeah, so this is kind of the main equivalence, which is kind of surprising that it actually worked out. So this is the actual kind of procedure that we follow. So first, we fix a J ferromagnetic coupling strength. Okay, we fix it just kind of for simplicity. We could vary it, but we just fix it for simplicity. Okay. Then for each theta H, so we choose some theta H that's say equivalent to the IBM experiment, and based on that theta H and that fixed J, we figure out what S here, anneal fraction, right between 0 and 1, works best for satisfying this equation. Now, in the actual D-wave machine description, right, the S steps are discrete and finite. So there's a little bit of inaccuracy in satisfying this equation, but we choose the S that fits this closest. Next, so again, this is just for a single theta H. So now I've selected an anneal fraction that works best for this simulation. Okay, now we select the annealing time, so TQA, that satisfies these two equations. Okay, so kind of the important thing here is that to get the actual equivalent evolution to what the IBM Trotterized circuit does, for each theta H, you get a slightly different D-wave parameter. So you get a slightly different annealing time and a slightly different anneal fraction. Yes. Okay, yeah, here's A of S and B of S. If you haven't seen this before, this is kind of what these schedules look like. This is specifically for Advantage System 4.1. Okay, this plot, yeah, this is a little bit too small. But basically, so on the x-axis, we have log scale annealing time. This is in microseconds. The y-axis is the anneal fraction. What we're plotting here is the full range of equivalent anneal schedules. So for the anneal schedule, what I mean here is the pause, not including the quenches, just the pause. How long is the pause, and what anneal fraction is the pause at? Having computed this for all of the theta H's that the IBM Q experiment originally did, and then each line segment is just plotting what that equivalent anneal schedule is for the range of theta H's. The reason that there's so many different lines is because there's a lot of different parameters you can choose different N's, so different Trotter steps, and different J ferromagnetic coupling strengths. Right. So the vertical dashed red lines, which are probably a little bit hard to see, but those kind of define this region sort of on the right-hand side of the plot. That defines the range of what annealing time you can actually program on this particular D-Wave device. So this is between 500 nanoseconds and 2000 microseconds. So all of the data within those two lines you can actually program on the device. All of the data that's outside of those two lines you cannot program. So for example, N of 5 Trotter steps, you cannot actually program on D-Wave. One slight caveat, you could program it on D-Wave if you set your ferromagnetic coupling strength to be very, very small. Unfortunately, that is actually outside of the quantization limit on D-Wave, so it does not work. So all of these annealing times are neglecting quenches. But quenches, like I said, we have to program into the system, right? So for all of these simulations, we have our ramps go as fast as possible. By that I mean there's kind of a maximum slope programmed on, set on the D-Wave software. This is the inverse of the minimum annealing time. So we ramp as fast as we can. That said, if your evolution time that you're pausing at, right, which is what this data is plotting, if it's, say, I don't know, a microsecond or half a microsecond, but your quenches are also roughly half a microsecond, then most of your evolution will be dominated by quenches. So one of the primary error sources in this simulation is quenching. There's other sources of error, obviously, but that's the primary limitation. And so, in particular, we think that data that's closer to the right-hand side of this plot, or I guess I should say parameter combinations that are closer to the right-hand side of this plot, produce better data. And the reason for that is because more of the anneal is spent during the pause and not in the quenches. And we'll actually see an example of this in the data. Okay, so this is the embedding. I won't spend too long on this, but basically there's a direct native mapping of the Heavy-Hex lattice on Pegasus, because Pegasus is quite dense. And so this is kind of doable. And in fact, Pegasus is so large as well compared to the 127 qubit Heavy-Hex lattice, we can embed it 6 times, that Heavy-Hex lattice 6 times. So each of those little kind of groupings are just the 127 qubit Heavy-Hex lattice being embedded again. And so this kind of reduces some biases that we might encounter in the anneal, but also we get more samples per anneal. And you can actually probably embed this more times. This is just kind of the easiest to do. Okay, here's a summary of the D-Wave QPUs. Number of qubits and couplers, how many times we can embed it. Yeah, the number of actual embeddings we could put on the device may have been less than 6 if we ranked like a missing qubit or coupler or something. Okay, right, so as I mentioned, the actual simulation that was performed was of a kicked Ising model. So what this means is your system is initially in the spin-up state. So for example, just pure forward quantum annealing would not do the equivalent simulation that IBM did. You need to prepare your system in some sort of spin-up state. Luckily, reverse annealing does that, right? So we can just program the annealer to begin in the spin-up state. We also tried another technique, which was just doing forward annealing with some pause at our anneal fraction that we need. But also using the H-gain field. So the H-gain field is kind of defined in this equation 9. The H-gain schedule is that G of t before the linear term. So this is a time-dependent schedule that you can specify. What this means is you can use that schedule to bias your anneal towards specific spin states by programming your linear terms and then turning on your H-gain field. Then you can turn it off, effectively setting your linear terms to 0. Yeah, and as I mentioned, all schedule ramps are as fast as possible to try to mitigate the effects of the ramp, or to minimize the total time that the system is in ramping. Okay, so this is an example of what a series of reverse annealing schedules looks like. So here the color bar at the bottom is denoting different theta h's, and then for 100 different linearly spaced theta h's, we're plotting what the derived equivalent reverse annealing schedule is. So the reverse annealing schedules are defined kind of conventionally. X-axis is the annealing time, y-axis is the anneal fraction. This is with reverse annealing, so we start with spin up state, then we go down to some anneal fraction, pause, and we quench. This is specifically on Advantage System 6.2 for 200 Trotter steps. So n is equal to 200, and using a ferromagnetic coupling strength of negative 0.001. Okay, yeah, the other thing I forgot to mention earlier is that to get equivalent simulations to the IBM experiment, and in the annealing time range that you can program and deal with, we really needed to use weak ferromagnetic coupling strengths. And what I mean by that is very close to zero. So the closer to zero you can get, actually, the better it is, because the longer you can, the longer your annealing time will be. So in this example for 200 Trotter steps, as you can see, the pause duration, it varies, but it's roughly at 10 microseconds, which is pretty reasonable, but it gets pretty unreasonable if your n gets lower, which we do run. So, okay, and then this is an example of what the H-gain schedule looks like. So this is on the left-hand side, we have our forward quantum annealing schedule with the pause, and then on our right-hand side is the H-gain schedule. The H-gain schedule, you kind of just barely see it, but basically we turn it on very, very strongly for a tiny amount of time at the very beginning of the anneal to bias it all of the spins in the spin-up state, and then we just turn it off for the rest of the anneal. By the way, the reason for that array is because the original Hamiltonian did not have any linear terms. Okay, so this is the first result plot. So the thing that I mentioned about the kind of smaller annealing times being harder to do, the kind of inverse of that is that larger Trotter steps are way easier to do. So this is kind of near the limit of what, like the total number of time steps that we could do. So this is 10,000 time steps. This is n of 10,000. The largest that the IBM Q experiments went up to was 20 Trotter steps. So on the x-axis, we're plotting theta h, but keep in mind that for each different parameter, this corresponds to different annealing times and anneal fractions, but we're plotting that equivalent theta h for the derived schedules. So each of the different lines are denoting slightly different parameter choices, so different coupling strengths, one of the two different quantum annealers, and using reverse quantum annealing in this HB method. The observable that we're actually plotting is just the mean lattice magnetization. So this is the average of all of the spins across the system. Yeah. So the one thing I should say is for this particular simulation and many of the other larger ones that we did, there were none of the classical simulation methods that came out, like the NPS simulations and so forth, moved to higher numbers of Trotter steps, and the IBM experiment certainly didn't. For this particular simulation, we actually don't yet have like a good classical comparison for how we expect this simulation to look like. We do have some simulations for 27 qubit systems, which I'll show in a few slides, but that's not for 127 qubits. So if you know of a good simulation method, talk to me afterwards. Yeah, and I guess the other thing that's kind of notable about this is that the shape of the curve basically you start out at a pretty strong magnetization of 1, and then it just drops to 0 very, very quickly. Okay, here's actual data from the quantum annealers again for 200 Trotter steps. So here we're seeing that the curve is less sharp than it was at the 10,000 Trotter step. We also start to see some disagreement between the simulation methods. Basically, different coupling strengths lead to different sources of error on the device. We think, for example, spin back the effect of all the quenching. All right, and here's 100 Trotter steps, kind of similar. We're starting to see now the data is a little bit more noisy. So at 100 Trotter steps, our pause time is maybe about 5 microseconds. But yeah, the data is becoming a little bit more noisy. And we're also getting closer to the regime of where IBM's experiments were. So the one thing I should mention is, in all of the previous data we looked at, we're looking at mean lattice magnetization, which actually none of the existing methods for like this particular system actually measured that. Most of them were looking at, like I said, polystrings or single site magnetization. So in particular, they arbitrarily chose one qubit to look at. So they looked at qubit 62 in the Heavy-Hex graph. So we looked at this as well at 20 Trotter steps, which was the largest that IBM did and kind of nearly the smallest that we could do on T-Wave. And at 20 Trotter steps, like I mentioned, we're getting very small pause times. And so we think that the effect of the quenching is kind of dominating all the noise. And so we tried a lot of different parameters, and you can see from this, sorry, it's not as large as the other ones, but you can see it's quite noisy. The data is quite noisy. What we plot against here is the original IBM Quantum data. So this is like the Z&E zero noise extrapolated data points. And then two classical simulation methods. This image I took from the paper, so the references are consistent with our preprint. But one of them is the Louisa classical surrogate simulation, and the other one is SPD data, which is one of the tensor network methods. I believe the title is like Fast and Converged Classical Simulation of the quantum utility experiments. So we kind of plot those magnetization curves against the D-wave data. So one other thing I should mention is here we also tried going to much lower coupling strengths. But here, so there the source of error isn't necessarily the quenches, although they're still there. But if you program your ferromagnetic coupling strength too low, then you're not setting all of your edges to necessarily all be ferromagnetic, and so the effect of that is that you're actually getting basically weaker magnetization. Like you're not magnetizing the full lattice. Some of them are set to 0, and so the effect of that is that you can get some magnetization curves that just don't follow the expected behavior at all. Okay, of these, we looked at root squared error with respect to the Louisa simulation, again, because this is like, basically the only comparison we actually had to the existing data, and that RMSE was using a J coupling strength of negative 0.003, using reverse annealing on a system 4.1, and that RMSE was 0.127. Okay, here's the classical simulation stuff I mentioned. So at 127 qubits, you have to do basically some type of approximation. What we did here, though, was we just looked at a Heavy-Hex graph that had 27 qubits. That you can just simulate using Qiskit pretty nicely. So we just ran the same Trotterization algorithm, circuit for this 27 qubit graph, and looked at the magnetization. So again, x-axis theta h, y-axis mean lattice magnetization, and we're looking at Trotter steps up to 300. We're actually simulating larger ones, it just takes a bit of time. And also here we have shot noise. This is 1,000 shots per data point. So, so the thing that we don't know is what happens as you change n, the size of the lattice, the Heavy-Hex lattice. What we see here is consistent with our quantum annealing results. Basically, the magnetization curve kind of starts out nicely symmetric, then it gets more and more squished to the left-hand side, where it's converging to a magnetization of 0 faster. That's consistent with the quantum annealing results. Again, this is only for 27 qubits, so we don't actually know. We haven't done the simulation for 127 qubits. And this is an example of the 27 qubit Heavy-Hex graph looks like. This is with the three edge coloring, and the gray denotes the bipartition. Okay, and one other thing that we can just look at, because we have the data, is the entire lattice magnetization. I have a couple of plots of this. We can kind of scroll through them relatively quickly. the magnetization across the lattice was pretty consistent. Here, theta h is small, so we start out near magnetization of 1, and then as we progress and make theta h larger, our magnetization on average goes to 0. Okay. So the kind of the one last thing that we looked at was, so first, like I mentioned, we don't actually have whole lattice magnetization data, say from IBM. All we have is single site magnetization data. And we also didn't have 27 qubit simulation data. And we also didn't have the raw data without the error mitigation, the zero noise extrapolation. So we just ran those trotterized circuits on all of the IBM hardware we could. So this is for 127 qubit and 27 qubit processors. Without any error mitigation, the left-hand plot is for n equals 20 trotter steps, and the right-hand plot is for n equals 100 trotter steps. So, yeah, without any error mitigation, you can see on the left-hand plot, most of the processors are basically half of what the magnetization is that we would expect, right? Because we start when theta h is small, we should have a magnetization of 1, but it's about half of that, which is roughly to be expected, like, based on existing calibration data and so forth. And then it does converge to a magnetization of 0, but it is pretty noisy. And at 100 trotter steps, it's just, there's very little signal at all, as you can see. So one of the reasons we wanted to compare against this is to kind of get a sense of where the processor, the digital processor was at without any error mitigation compared to what we could do with quantum annealing. Oh, and also this shows a good comparison between this 27 qubit magnetization versus 127 qubit results. And we see that the results are pretty consistent, although the data is pretty noisy, so it may be hard to tell differences anyways. Right, so this data is kind of one of the first things that we looked at, which was just, so this plot is not equivalent to the existing IBM Quantum simulation. This is a bit of a different thing. So here we're just fixing the total annealing time, and then on the x-axis we're varying the anneal fraction, and then on the y-axis we're again looking at the mean lattice magnetization. So this is, like I said, this is not equivalent to the IBM Quantum experiment, because here we're not varying, changing for different theta h's what the annealing time is and what the anneal fraction is. This is, I guess, in some ways a more straightforward kind of simulation of the system, which is just a fixed ratio between your programmed Ising and your transverse field Hamiltonian. And you can see that the response curve is pretty nice and symmetric. I guess as expected. Oh, right, so the other important thing here is we again use a weak coupling strength, J of negative 0.001. One of the things that we observed, so for the equivalent IBM quantum simulation data, if we set the coupling strength to be quite large, like near the limit of the largest strength that we could program in the processor, that equates to too fast of anneals, so we can't do it. But for this scenario where we just fixed the annealing time, we did also try these very strong ferromagnetic coupling strengths, and one of the things that we observed was quite a bit of distortion when the coupling strength was too large. So like in particular, we think the spin-back polarization effect had a significant impact on the results, because we got like quite noisy, high variability results. And those plots are in the preprint if you're interested. Yeah, so I guess the overall takeaway of this paper is basically that we think that using analog quantum simulation, you can perform reasonably good simulations on par with what the IBM Quantum hardware demonstrated. Now, the caveat of this is, in the case of the D-wave quantum annealer, for example, we couldn't look at the observables of other Pauli strings, right? Because we don't have universal control, like switching the qubit into some other computational basis. And so that's the limitation. But we were able to go up to equivalent time steps that were like orders of magnitude more than what IBM could do. And yeah, acknowledgement implements use of IBM Quantum, funding from Salamos, and lots of helpful discussions with Tamim Albash, Mark McFray, and Carlton Cochran at Los Alamos and UNM. And thank you so much for your time. Let me know if you have any questions.
Thanks. Any questions?
Thank you for the talk. And actually, I was curious, you didn't apply any error mitigation scheme, right? In the D-Wave, in the case of the D-Wave.
Correct.
But actually, you know what the main source of error is, which is this RAM, right? The initial RAM. And you can increase it and then reduce it and do the extrapolation that they use, useful, like 0 point extrapolation in this case would be possible, right?
Yeah, definitely. So I think there was a preprint released by D-Wave maybe a couple of days ago on like developing error mitigation techniques for quantum annealing. Yes, we didn't use those. There's also like even just some, improvements of like calibrating, say, the flux bias offsets and things like this. There's definitely many new things that could improve the simulation on D-Wave. We did not do any of this. We did use server-side spin reversal transforms for the H-gain schedule method. The other thing about the H-gain schedule encoding technique is that in principle, it should mitigate the effects of the initial ramp. The reason for that is because the H-gain field is still being applied while the ramp is happening. And so the spin-up state should be, in principle, like all the spin should be in the spin-up state when the pause begins. But that doesn't mitigate the effect of the final ramp. And yes, your idea of kind of varying the ramp duration is an interesting one. I don't actually know what the effect would be, but very well there could be something to extrapolate there. I guess in principle there should be less distortion when the ramp is longer.
Okay.
Yeah, there's many ways to potentially improve the simulation.
Maybe while you were working on this, have you discussed it with any of the IBM people, or have you had any reactions from them already?
I have not personally gotten any reactions yet from them. Let's see. No, we did not email with the authors of the IBM paper about this particular experiment. We did email with them discussing getting data because we wanted to kind of compare our results against theirs, but that's it.
Okay, nice, thanks.
I have a question here. Thank you for the talk. Over here. I'm trying to wrap my head around the parameters that you mentioned that you did. Because you said J to something like 1 part per thousand or 2 or 3.
Yep.
Is this measured in the units that are listed on the D-Wave machine? So that's a number that maximally can go between -2 and +2.
Yes. So it's in units of joules, I think.
But then, how did you deal with that about 0.05 fluctuations on setting of those parameters?
Right, yeah, so basically, well, I mean, yeah, short answer is we didn't. So the thing is that for all of the couplers on the D-Wave chip, let's see if we're getting this right, it's like every coupler can have a different quantization, but each strength is also deterministic for each coupler, and there's a distribution across the entire chip. And so, yes, exactly. We did not, so like for example, you could in principle go through kind of each coupler you're using and like try to figure out what the exact weight it is and maybe calibrate for that. We do not do any of that. We're just essentially assuming that like if it's sufficiently above the mean quantization should be ferromagnetic. But yes, there's also, there's a number of calibration things that we didn't do. They're just basically too low level. I think one of the issues was we don't actually have the data of what the exact values are for each coupler, right? We kind of have to calibrate that ourselves.
So perhaps to follow up on the previous comment, maybe you should contact D-Wave to give you that data. Because effectively you are plus or minus 0.05 and then anything on top of it. So maybe as a follow-up, is there a way of actually increasing J at the sacrifice of other parameters such as you're less affected by that fluctuation?
Sure. By the way, you said 0.05. I think it's less than that. I think it's less than that by an order of magnitude or two. I don't think I remember the exact numbers off the top of my head, but I think it is less than 0.05. The kind of the distribution there.
0.05 is what I had from Victoria. I haven't measured it myself.
Sure. Yeah. I think maybe also it varies by which device generation it is.
It could be machine specific.
Is that right? Okay, so the trade-off is, and this is essentially because of kind of the way that IBM set up the experiment, but the trade-off is, so they coupled N and J together, and so the trade-off is you can go to larger J's, but you need faster anneals, and in particular, so like on this plot, it's hard to see, but basically the maximum, or rather, I guess the minimum, like strongest ferromagnetic coupling strength you can set requires all the shortest anneals. So that's all of the lines that are at the very bottom of this plot. And so the trade-off is if you go stronger in your ferromagnetic strength, you need faster anneals.
We have a look at page 23 where data of both processors have been plotted onto each other. So which is
Okay, yeah, so IBM data.
the dots.
Yeah, they're like the big
simulation results are. So what's the source of differences?
In the D-Wave data. Right, okay, so each parameter setting here corresponds to different annealing, like series of the sequences of annealing schedules, right? So we're trying different ferromagnetic coupling strengths, and that results in different annealing times. And so we get different effects of the ramps. And then if our coupling strengths are stronger, that could also lead to things potentially like spin back polarization. And then I guess the other main difference is some of these simulation methods are using H-Gain's schedule method plus server-side spin reversal transforms, which should mitigate some local biases, whereas the reverse quantum annealing is not doing that. But
So those differences in the choice of parameters affect the results significantly.
yes. Now, so basically, so for context, like the pause time here is so if we increase our J coupling strength to -0.004, some of this is for -0.003, you cannot program it on D-Wave. So we're right at the limit of what you can actually program in terms of annealing time, so the pause times are like maybe 500 nanoseconds or so. These are extremely fast. So the differences here are extremely magnified. But if we go to like 10,000 time steps, the results are much more heterogeneous or homogeneous because, basically the evolution time is long enough that it kind of is the same.
So my colleagues at D-Wave have a couple questions for you. One is, do you plan to go more than 127 to try this on larger graphs, or than 127 qubits?
Yeah, it's definitely possible. I will say that basically this thing is kind of, so basically the Pegasus coordinates are kind of difficult to deal with. This I kind of had to essentially hand code. So yes, it is definitely possible. I think you can probably go up to like I don't know, probably 1,000 qubit Heavy-Hex graph, maybe more. Yeah.
And the other question was, well, not so much a question. Andrew King says, with great respect, he thinks he can find 7 rather than 6. So maybe you should talk to him about your graphs. But I guess from hearing your talk, you could do that, but you don't have anything to compare it to. The IBM machines can't go that big, and it sounds like maybe the simulators couldn't either, the classical simulators.
I believe the authors just didn't try it because they didn't need to. Yeah, I actually put in like a paragraph at the end of our paper that basically said, please try this for, please try this for classical simulations. I'm pretty sure they could, NPS simulations seem extremely efficient. I think they could probably go up to at least a couple hundred or 1,000 or something. That seems pretty doable, I think.
And my other question was, do you know of any other examples where the quantum annealing was used to simulate the simulation of it's just simulate gate computations in this way? The half theta over 2. That seems I've not heard of it before. I'm just kind of curious whether you have any prior work in that area.
Not that I can think of off the top of my head, but I know that there's definitely been, like in fact there was a preprint about a month ago for simulating TFIM on a Kagome lattice on the Zephyr prototype. Now that didn't have a prior, a digital gate model simulation, but there's been a lot of stuff about magnetization in particular. You can do lots of interesting things with like the H-beam schedule and all of this for systems, for like TFIM systems. But yeah, not that I can think of off the top of my head, but I'm sure there's probably at least a couple examples.
Yeah, interesting. That's why I said novel application of quantum annealing struck me as a new way to use these machines. Anything else? Once? Twice? Thrice? All right, well, let's all thank the organizers. Thank Paul and everybody. Stand up and be acknowledged.